the cool part about imaginary numbers is that although in high school we don't see their application much, in college courses you really do. So if you think about, I think I've talked about feedback systems before, like an air conditioning system. I was looking right at it, which you saw. And I think I mentioned even earlier this year that there are a lot of places in controls and systems in engineering, like for stabilization of a plane, or your car to have what's called slip differential. So if your car is going around a turn and there's water on the right side, your right tire might just spin continuously because it doesn't have the same traction that the left tire would have. So there's what's called a gear differential. So one of the like half the axle can spin at a different rate than the other half. You think the axle is continuous throughout the car. And again, these are locations where imaginary numbers are used a lot. It's a topic that you'll see now, and then you'll see its applications pretty much after calculus. Is that understandable? Okay, so don't be like, oh, we're never going to use it right now. But you will if you take a little bit of math. In calc, you'll use it for sure. For like Euler's equation and a couple others that use imaginary value. But the applications of it you'd see in like a science, engineering world. Probably, obviously, as a math major also, you would see use of it, but I don't know how many applications you would do if it would be more theory. So we're looking at the square root of negative numbers for this. So this was the equation that was considered at first, and we did this earlier with square roots. We said x squared equals b, and that solution is where the square root came from, the solution to that equation. So the solution of this equation is where the, what we say, imaginary number, or the constant I, was invented. So we want to think about, well, how could we get an answer to this? And obviously, what's the answer? We're going to say, well, x equals plus or minus the square root of negative 1. And we've been saying the whole time that, well, the square root of a negative is a non-real number. But this right here is our definition of I. So we can say that the solution to this equation is simply plus or minus I. Now, where does that come from, actually? Well, it actually comes from the fact that the definition of I squared is really negative 1. Another important part that we'll utilize. And if we think about this, really, if we take the square root of both sides, God bless you, if we take the square root of both sides, we get the square root of negative 1 equals I. And again, it's plus or minus here. So, by definition, I takes the place of this radical here. But really, it's because of this fact that I squared is equal to negative 1, square root this side, square root this side. Well, that's the constant I by definition. And this is one of the weird ones that you kind of just have to accept because it was made up. Versus like the constant E, you'll learn about where it comes from. It's a limit process. Or pi, circumference to diameter, that ratio is where pi comes from. It's not like a number that we kind of like invented there. It's a ratio that constantly occurs. The golden ratio, another ratio in nature that occurs all the time. This I constant here, though, is just a definition for this square root of a negative value. And we need this, because if we don't have this, when we get answers with negatives, which we will eventually, we wouldn't be able to go anywhere, right? We'd stop and say there's no answer, but really there is. There's a way to express that answer in terms of I. Now, one thing that's important to note is this. There's a pattern with I. And you'll pick up on the pattern and notice it. And let me write it out to start first. So anything to the 0 power is what value? Any number, any constant to the 0 power is always 1. So I could start by saying I to the 0 is 1. And that's true. I to the 0 is definitely 1. But then I can say this. I to the 0 is 1. Well, I to the first, and that's by definition, is just the square root of negative 1. This is really simply just I. So what I'm going to do is I'm going to go through a cycle, a cyclical process. So what would come next here? What would I squared be by definition? What we started with, the definition of I squared we used. It's on the board, so I'm not like trying to make this one up. What's I squared defined as in the top right? Negative 1, right? So that's our next part. And then finally, I to the third. Well, let's think about what I to the third would really be. I to the third would be I squared times I. Does that make sense? But what's I squared by definition? What do we say I squared is? Negative 1. From over here, right? We know that I squared is negative 1. So this is negative 1 times I, or simply negative I. So that's what I cubed is. And we can kind of derive it every time by splitting up I into two parts of which we know. Does that make sense what I'm getting at there? We can break it up like that using our laws of exponents. Because we know I squared, it simplifies things a lot. So this becomes negative I. So the wheel turns like this. And then try I to the fifth. Prove to yourself that I to the fifth will end up, I to the fourth will end up right back here. What is I to the fourth? What can you break up I to the fourth into? What would you break up I to the fourth into that's logical?
-1 times -1.
Yeah, and what's the, but before that it's I squared times I squared, good, which is -1 times -1. But what's negative times negative? Clearly positive, right? So I to the fourth is -1. Doesn't that value, it's +1. Doesn't that value here go back right to the beginning of the wheel there? So this corresponds to this value for I to the fourth. And then I to the fifth will go here, I to the sixth, I to the seventh, I to the eighth, and it continues around. Now you're probably saying, like, who cares? There are certain times where you can get I to a higher power. It's not going to be the end of the world. If you don't have this memorized, you can derive it every time. If it's a non-calculator question, you kind of got to know it. If it's a calculator question, there are ways of the calculator to figure that out, but your mode has to be changed so that it actually works with imaginary numbers. Because as of now, if you take a square root of a negative, it always says error, non-real answer. That's the command you get in the calculator. So this cycle continues. Now, can you pick up on a pattern? Obviously, it's by 4, right? Notice that? So logically, if I wanted to keep working around the actual cycle here, and I'd say, okay, that's out of the 4. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, there's 19. So I'm just hypothetically saying, if I wanted 19. So out of the 19th is really over here. So out of the 19th is really out of the 3rd. So it really simplifies to be -I. But do I want to count around every time? Is that a mathematical approach? No, it's like, a 5th grade approach where you start learning how to count and pick up on patterns. How would I figure this out if it's I to the 19th? How do I to the 3rd and I to the 19th, what do they have in common? Anybody pick up on it? This is a little bit odd, I know. Oh, weird, not multiple items. Yeah.
It's an even number with no leftover, so the leftover will make it negative and all the evens would cancel each other out.
So, yeah, you're on the right track. It's something like this is I squared with an I, and this is I to the 18th with an I. So the even part can help for sure, but you could run into a little issue because this one would also fall into the same category. But that's a good approach to start. If we can specify that a little bit more, we'd have a good approach, or a completely foolproof approach. That one could run into trouble. Yeah,
I mean, the number in the ones place is divisible by 3. I don't know if that.
the number in the ones place is no, but I like that. That's a good pattern. This is 3 and 9, right? They're both divisible by 3. Divide these both by 4, because the cycle goes by 4, doesn't it? What's 3/4 as a decimal? 19 quarters. 19 over 4. Huh. As a decimal, 19 over 4 is?
It's like 4 and 3 over 4.
Yeah, so 4.75. So what do you notice is that if you take that power and divide it by 4, the decimal you get for I to the 3rd, if you get a 0.75, it means you're on this one here. If you get a 0.5, you're over here. Divide this by 4, don't you get 0.5? Divide this by 4, don't you get 0.25? These are ways in high school that I made like mnemonic devices now. Obviously, you can also take out I to the 16th here. Because isn't I to the 16th right? Because this was 19. 18, 17, 16. Everybody see that? So I can take I to the 16 out of here, and what's left over? I to the 3rd. So pretty much you can either do one of two things. You can divide the exponent by 4 and look at the decimal and see what it corresponds to, which decimal spot. So if it was I to the 35th, divide that by 4, that's 0.75, it'll end up here. I don't care what the actual integer is in the front, right? I care about the decimal part. Or I can think of any multiple of 4. 4, 8, 12, 16, 20, 24. Take those away from the number I want. So if I think about I was just saying I to the 35th, what multiple of 4 is below 35? That's just 32. Take away 32 from 35, what are you left with? You're left with 3. You're going to go back in this spot. So again, if you want to just take away a multiple of 4 from the exponent, or divide the exponent by 4, the whole concept is that it works by 4s, the pattern. Patterns are good to pick up on, and like if you want to practice these kind of things, you could look at like riddles and like number challenges and stuff. It could actually, I mean, it does help your brain, and you're going to see a lot of this with sequences and series where you have to pick up on the pattern, whether it's geometric or arithmetic. Like 2, 4, 6, 8, 10 is a pattern, right? But then I could also think of towers as patterns as well. 2, 4, 8, 16, 32, 64. But pick it up on the pattern is what we're doing there. All right, let's take a look at some quick examples. We went over this already. Let's take a look at this first example. So the square root of negative 36. What do I think of this as? Well, I think of this as the square root of negative 1 times the square root of 36. All right, that's really what it is. And the square root of negative 1, we said, by definition, is now I. So this is I times 6, or simply 6I. So part B, what would you do? It's not a perfect square, so how does the approach change? Adapt?
Radicals.
Yeah, we're going to leave things at radicals. So what do you break it into, Sean? Give me a breakdown first.
Square root of 32, square root of negative 1.
Okay. Go ahead, next one.
So that would be I times,
And I want you to break it down so people see, make sure we're good.
what would be 6 square root of 16 square root of 2,
Good?
which is 4 radical 2. So it would be 4I radical 2.
Nice. Good way of writing it, too. Radicals always go on the edge. Now, I will talk about how, with complex numbers, should be on the far right, and we'll discuss why that is as well. Let's go to the second example. So, simple ones again, but thinking about complex number sets. So the square root of negative 64, we don't have to break it up right anymore. We can figure out, obviously, right away. Since 64 is 8, this is just going to be 8I. And then minus here, the square root of 100, 10. So we put the I at the end, so negative 2I. So what I want you to see is that your laws of addition and subtraction hold true as if they're, as if these values are like terms, like variables. So if you had 8x minus 10x, it's the same thing. Same thing holds true there. And then the 8 and the 18, we have to consider also breaking down. So what would I break this into? Just to get our quick practice in for our square roots, John.
4 and 2.
Good. And the second part. What do I look for, right? Clark, what do I look for here?
9 and 2.
Yeah. And the goal is to get another 2 there, most likely.
Wait, why is the I under the radical?
It's not, I'm sorry. Let me close that radical. Oops. Yeah. I can close the radical a little early and put it on the right, but yeah, I'll put it in the right order at the very last. So here we have, we're going to have 2I plus 3I, both with a radical 2. So we'll have 5I radical 2. Yeah, I do this a lot. I don't know. I mean, it's something in college I picked up because sometimes your radical can carry over enough, so I put a little close there. So it might help for that. Let's see. All right, so number 3 is interesting. So take a look at it on your own for a second and come up with some sort of correlation or some sort of almost a rule, I guess you would say. So look at part A first. And check it with your neighbor, actually, because when you see different answers, we're going to pick up on something. Because I guarantee you we'll have multiple answers for part A. So when you're done, just compare with the person next to you. See if you got the same answer. If you didn't, discuss maybe why. If you did, that's fine. And we'll discuss whether it's right or wrong. Simplify as far as possible, always, right? As far as possible. You could go on to B if you'd like to, so check your answers for A with each other. And that would replace that, because that says I swear.
Oh, I thought you did a loser one. You just said that. Oh, yeah.
It's either version of 1 or version of I. That's the whole section. So this is 1. I.
Oh,
Correct. So I Good, same answer. Good. Good. All right, nice. Nobody fell into. There's an unfortunate trap you can fall into here, and I can see why you can fall into it possibly too. Good. Nice. So, and I'll show it to you actually, because you might do this by accident on a test and think, oh, so I can do this because we've done it earlier, but you can't do it here. Anybody know what the unfortunate trap is that I'm going to talk about?
Leaving it as I squared.
No, because that's just not simplifying. That's not correct. You're right, Sean. It's not simplified as much as possible. So we know, I walked around and saw you all. It says 3i times 4i is 12i squared, but I squared is -1. So everybody seems to get this, which is really good, actually. I was happy to see. The rule from earlier on was that we could also multiply what's under the square roots first. And it's not logical to do that here because these numbers are nice and perfect, right? But if I had something like this, it might be a little bit tempting. So let's say I had the square root of -8 times the square root of -2. Isn't it tempting to multiply those first? Because what's 8 times 2?
16.
And then that makes it a perfect square. It's much easier than breaking this up and carrying down. Does everybody agree with that?
Yeah.
But I can't. Clark?
They're both negative, so it would be positive.
Okay, that gives me the square root of +16, which is what?
Just 4.
Just 4. So what are we missing, Clark, if we do this?
The imaginary.
The imaginary I squared, which makes the answer really, I squared is -1, so it makes the answer -4, actually. This is one of those times where it's not a principal square root issue. It's not like we're solving an equation with plus or minus 4. But here, this really, the correct way to do it, I'll show in red, would be again to make this the square root of 8 times I times the square root of 2 times I, to take your I out first. Not take your I out. Anybody ever seen that? Go shoot your eye out from Christmas Story? Root 16 times I squared. This becomes 4 times -1. And therefore the answer is actually -4. So make sure you write yourself a note that this is not correct. And I think I put that on the next slide. If you go ahead and look on the next slide, you'll see that there. I think I wrote it. If not, I can jot down my exact wording for it. Okay, but we cannot multiply things under the radical if they're both negative. If one is negative, would it work? Yeah, how come?
Because a negative times a positive is still a negative.
It's still a negative. And having a negative will still give you I, which you would have had even if you didn't put them together, right? So you hear that what John said? If you have one of the radicands negative and one of the radicands positive, you can multiply underneath. It's when they're both negative, you can't multiply underneath and drop the positive and drop the negative. Okay? You all right? Okay. What about the second one? If I break this one down, multiplication again. And think about this logically. I would not multiply 32 times 12, right? We know that one. Sean, go ahead.
Before I radical 2 times 2I radical 3,
Okay.
and that don't think you can simplify that.
Careful, it's multiplication, not addition, right? Multiplication tells me when I have radicals, I want to get, you got it?
Under, so treating this stuff, so it would be 8I squared radical 6,
Yeah, which is really,
-8 radical 6.
okay. Check your working part, I know somebody did part B already, so just go through it quickly, but again, break it down, recognize outsides multiply outsides, insides multiply insides, get an answer, simplify. Again, I squared is -1, which is where that's coming from. Okay. At the bottom, I wrote the actual rule out. And think about it this way. You can say that A times B is not equal to root AB if A and B are less than 0. And that's what I was saying earlier, okay? Again, multiplication of A times B underneath is not true or not valid if both A and B are negative numbers. If they're both negative. If one of them is a negative number, though, that rule holds true. Now that rule definitely holds true if they're both positive numbers, and we showed that in the last chapter. So the note that I was going to write down that you can jot down if you want to on the previous slide is this. So think about this one, and I want you to see if you have an idea of doing this. And I know some of you have maybe seen this stuff. If you do, if you have seen it, just try to put the answer down. But others, think about it for a second. Think about the technique for rationalizing a denominator. When we had like radical 3 in the denominator, what did we do there when we had like a radical 3 in the denominator? We multiplied by radical 3 over radical 3. Good. So what might I do in this problem? Yeah. Yeah, why don't we start by trying multiplying by 5i in the top and the bottom. So we'll get 15i up top over 25i squared in the bottom, which will give us 15i over negative 25, which we can then simplify to negative 3i over 5. So what was one thing I could have cut out to make it a more efficient process that we picked up? What do you got, Altea?
Could you just multiply by I?
Yeah, I works by itself. So the 5 is not needed. But I want you to see that because that's what you would have done with radicals, right? So the I is the only thing that's really necessary. You don't need the 5 there. Okay, you don't need the 5. And if you don't have the 5, you get directly to 3i over 5i squared, which in this case becomes negative 3i over 5. And notice what I'm doing. I'm taking the I squared that's here, making that negative 1, which is here. Then I kind of put the negative up top. I'm allowed to do that. I could also put the negative out in front. The whole concept is that it's a negative quantity because of the I squared value. Yeah? How about part B? What do you got, Sean?
Everything by square root of negative 3 over square root of negative 3.
That'll work.
So you would have 4 root negative 3 over 3.
So we'd have 4 times the square root of negative 3.
Over 3.
Now, where does the 3 come from, just so we're all aware?
Negative 3 times negative 3 is 9 square root of minus 3.
What did we just say, though, Sean?
What?
What did we just say a minute ago?
Can't do that.
Can't do that with negative numbers. It's okay. You got it right, though, so far. So what do I do instead? I can't do negative 3 times negative 3 and make it 9.
They'd be over negative 3 because you have to add the i's.
Yeah, the i's that come out of here and here leave this with 3 and 3. So let me show that, okay? Yeah, but you're on the right track there. Good. So what we'll notice here is that this part right here is really I times root 3, and this is really I times root 3. And now I can multiply the 3 times the 3, which gives me the 9, and the square root of 9 gives me a 3 here. But I times I is I squared still. So I'll write it out. So this becomes that. Then what we end up getting here is I squared times the square root of 9. The numerator leave alone still for now. The denominator becomes negative 1 times the square root of 9, which is 3. Again, this is negative 1 times the square root of 9. Negative 1 times 3 is negative 3. Do I want to leave this way, though, as an answer? Probably want to take out the I out of here as well. Okay, so we go ahead and take that I out at the very end. This will become 4 root 3 times I all over negative 3. Now, you'll notice that I'm not being consistent with my writing for the way I set up with I here. Okay, this one I put a coefficient in front with a negative in the bottom. Here I made the whole thing a fraction with the I up top and the negative. I'm doing this on purpose because I'm noticing more and more that students are forgetting like their fundamental skills at times. That this I obviously out here, you can think of this as a coefficient. It happened on the midterm a couple times. You can think of this whole thing as a coefficient. Remember the problem with V equals 1/3 pi r squared h divided by the component? For that problem is what we would think. So out in front or put the I up top, either way. Think about that. Now, with the next part, let's see, actually with this one we're not going to have to worry. With the next part it's a little bit different. We don't have to worry too much. So what if I have things with variables now? And we assume that each variable is positive real numbers. So we don't have to worry about the absolute value. Remember that absolute value concept coming out? So because the variables are assumed to be positive and real, we don't have to worry about that. How would I treat part A? How would I treat part A? Notice A is obviously the easier one, B is the harder one. How would I treat part A? What would I do here? Yeah.
Split it up into
works. Okay, continue.
Plus -1 times 9x squared.
Okay, I like it.
And for 9x squared, that would be 3x.
And then the square root of -1.
Is I. And then it's 2x.
Good.
Square root of 4 squared, and then I again.
Very good. Therefore,
Would be 5xi.
nice. Good job, guys. So we're breaking it down into perfect squares again, as we've done before. And then the I is separately done here. Square root of -1 becomes that I. -3x. We have simply 5xi. Good, like terms. How about part B? Part B, similar to part A, right? Similar to part A. What are we thinking for part B? I'll give you a minute to look at it. There's a starting point. If you're having trouble getting started with it, you start with that idea, and then move to that. Again, don't forget to take that I out right away. And lose that negative sign in the answer. It should be there.
Would it be, so once you have the I and the I on the outside, you multiply those I squared with -1, and then multiply 6y times 3y, and you get 18y squared, and then you have, take out the 9 and the y, and so you have y squared, and then you have -3y root 2.
Good job.
Do you need absolute value?
We assume that the variables were positive in the beginning, so we don't need them. This statement here, remember, tells us that we don't need absolute value if we assume that the variables are positive. And that has to be given in directions. Okay? Take a look at the work, make sure it makes sense. So we're combining a lot here. That's what makes these a little bit complicated, right? Because we're combining techniques. We're combining simplifying radicals with imaginary numbers, with rules of exponents. I mean, all of these things are involved in one problem now. So you can see how there's a lot of maybe room for small mistakes. So we need to be very meticulous with our work. All right, let's finish up today with example 6. So let's go ahead and solve an equation with this now. And we're going to lead this into our next chapter, really. We're going to be doing a lot with solving equations that involve imaginary numbers also. So if I want to solve this one, I'll move the 25 over first, right? Divide by 3. Take the square root. And then break it up. I'll think of root 20, right? That's negative 20. I'll think of root 20 as 5 and 4, taking the negative 1 out as an I. So I definitely have an I there. Plus or minus. I've got I root 20, which is really plus or minus I times root 4 times root 5, which is really plus or minus 2I root 5. Okay? Yeah?
Why do you need the plus or minus sign for this?
Why do we need the plus or minus for this one? Does it answer that? What are we doing in this process right now, this problem? Olivia? We're solving, not simplifying. And when we solve a quadratic, we must get two answers always. Remember, the degree of the polynomial will tell you the number of answers you get. The number of solutions to the equation is always indicated by this degree for any polynomial function. Some of those answers will be imaginary. And notice we got how many imaginary answers here? Two of them. It's not a coincidence. We'll always get two. You can think about that for a little while, actually. Let that ruminate. We'll always get two imaginary answers. We'll never get one by itself. We'll never get one imaginary answer by itself. I'm talking about to polynomial equations. So if it was like x to the fifth, we could get 3 real answers and then 2 imaginary answers. If it's x to the fifth, we can get 1 real and 2 sets of imaginary answers. But they're always going to come in pairs. Just keep that in your mind. We'll talk about it in the next couple of days, but give it a preview. Anyhow, homework for this. Let's take a look at the